the next talk. We have Vsevolod Yashin with Lie-algebraic approach to one-dimensional translationally invariant free-fermionic dissipative systems.
Okay, thank you. I will start. First of all, I shall thank the organizers of this conference for the opportunity to present my work. And this talk will be based on my joint work with Levy Becker, Denis Kurlov, Fedorov, and Gritsov, which was published in 2020. This work is about a solution to a quite general physical model, basically a quadratic fermionic translationally invariant chain. And I plan to, first of all, talk about this model that we are interested in. Secondly, how this model could be solved using some Lie-algebraic techniques, the famous Wei-Norman method. And finally, I will give you an additional information about how the spectrum of this system, the generator of this evolution, could be found, and in case when the dissipative gap closes. First of all, there is a famous theorem which states that every open quantum systems evolution on open quantum systems are described by the Garini-Kosakowski-Sudarshan-Lindblad equation. D rho times dt is given as a sum of action of Hamiltonian plus the dissipator. This whole generator of the evolution is called usually a Lindbladian, or in our case a Liouvillean. Now, due to the theorem of those four people, the dissipator has the form of this time. It is a sum of the L alpha minus 1/2 of the anti-commutator of this thing, and those operators are usually called jump operators, or some other kind of operators, Lindblad operators, Krauss operators, and so on. We will consider a physical system that is a fermionic chain with periodic boundary conditions. The Hamiltonian will be given as a sum of creation and annihilation operators that satisfy canonical anti-commutation relations, and also this part. Here in this equation, mu is the chemical potential. Tn describes the hopping between n and between sites j and j plus n, and gamma n describes p-wave pairing between sites j and j plus n. Plus, we also have a Hermitian conjugate part to this thing. So the Hamiltonian is self-adjoint. Now, the dissipator in our case is described with jump operators as sum by n, uj minus n, cn, vj minus n, cn dagger, where ux and vx are some kind of functions, which are we can note that this, in fact, is the most generic structure for translationally invariant and quadratic fermionic chain. Now, since this we have the translation invariance, we want to do the Fourier transform of this system. So in the momentum case, our Hamiltonian reads as sum over the momenta in a Brillouin zone, which may depend on the number of sites we are considering, but basically we want the thermodynamic limit. And this sum has the following form: sigma k ck dagger ck and these things. So ck is described as mu plus 2 tn cosinus, has this form, and delta k has this form. Now, if we take the Fourier transform of dissipator, we will have just the Fourier transforms of those parameters. UK and VK are Fourier components of UX and VX from the previous slide. We also note that Hamiltonian and dissipator are presented as sums of HK and DK, and all the Liouville part that correspond to the momentum K commute. So for each momentum, we can solve the equations separately. We shall do it. Now, note that because we everywhere we only have a quadratic number of creation and annihilation fermions, so we can look at the following set of super operators. X1, X3 will be n plus minus k, where n is the operator of number of particles. The minus 1/2 part just corresponds to the normalization for our convenience, and all other super operators denote various parts with quadratic, which are quadratic on creation and annihilation operators. Then, if we choose the Lie-algebra structure of just a commutator of these super operators acting on ρ, then this set of super operators are Lie algebra. In fact, here is the table of which shows the structure coefficients of Lie algebra. For example, if we commute x3 and x5, then we will get minus x5. And as you see in this table, there are quite a lot of zeros, though this algebra is quite good, and we can compute something about it. Now, the Liouvillean, as shown here, could be presented using those super operators in this way. So that is quite a long expressions indeed, and we can find that each super operator takes place in this relation. There are no zeros. Also, here are some constants which are defined for convenience. Now, let us consider the structure of this algebra. Since it is finitely generated, we could solve it for using the techniques of Lie algebra. And in fact, we can show that this algebra has a radical, an element y0, which commutes with each other elements. And the second part of this algebra is just the SL for on C. And this algebra has generators like this. So once again, those super operators generate the SL4 on C algebra, and here this part Y7, 9, 8, and 9 are the Cartan subalgebra, the maximum commutative subalgebra in this algebra, and uh, the elements prior to the Cartan subalgebra will be negative roots, and after the subalgebra will be positive roots, or actually vice versa. I don't not actually, exactly remember now. Um, Once again, the Liouvillean could be rewritten in this form. Lk is minus lambda k of t divided by 2 plus the generators from 0 to 15. Once again, there are no zeros in this sum, and the parameters are shown here. Next, as we see, the generator of our evolution, the Liouvillean, will be given as a sum of generators of Lie group, Lie algebra, but there is a well-known method called the Wei-Norman method, which could solve problems like this. So Wei-Norman created this method in the 60s. They had two papers on it, and the idea was the following: suppose there is an Lie algebra y1 to yn, and we want to solve the equation d by dt s of t equals L of t s of t. Here S is just the fundamental solution. We consider it to be some kind of matrix, and L is our Liouvillean. And for those we want for this equation to have a form where L of t is a sum of AK of t and YK, a sum of generators, and the fundamental solution equals the product of generators, exponents of generators with respect to UK. Now let me present this method by differentiating the S of t with respect to this formula. We get a sum L from 1 to n UL dot times the product of all exponents before the YL and the product of all exponents after the YL. And next, if we additionally get the exponents of from 1 to L minus 1 here, then we will get this expression, the S of t, and this will look like this, and finally getting various coefficients here, we can show that d times dt of S of t is a sum from L1 to n of dot UL dot times the product of exponents less than L, which act on YL, and then S of t. That means that L of t has this form, and that form, and on the left hand side we have as earlier the sum of generators. We could expand the action of each YK on YL and obtain formula which is linear on y dot, and probably it is dependent on t and u, but on the u dot a is linear. Then we could solve this set of equations with respect to a, and then integrate. So we would get from a k out of t the solution u k out of t. In fact, it was shown in the paper of two Polish authors that in case our linear algebra is SL, this method is especially good because it leads us to have only the Riccati coupled equations. Now, in our case, it came that Riccati equations look like this. There is a one set of Riccati equations. We should solve it, and another set, and so on. We have even more Riccati equations. So that shows that we can solve for each k. Our system, we can transform it from the system of linear equations to the system of coupled Riccati equations, and we also may hope that these equations will be better in some kind of numerical sense or in other sense. Now, we also can directly vectorize and then diagonalize the Liouvillean. After a number of computations, it was shown that the spectrum of the Liouvillean contains 16 eigenvalues. The first one is 0, a trivial eigenvalue which always holds, and then there is eigenvalues lambda 1, lambda 4, lambda 5, which are non-trivial, and all the other eigenvalues are sums or the complex conjugates of them. Here are some parameters which are used to shorten the expressions. Knowing the spectrum of the Liouvillean is obviously a nice thing to know, and the general arbitrary Liouvillean spectrum looks something like this. We have a set of points on the complex plane. There is a trivial steady state for the eigenvalue 0, and some oscillating coherences that are this subsystem evolves like in unitary way. Afterwards, there are also some eigenvalues which have the real part, the negative real part, and the least the distance between first negative eigenvalue and the imaginary axis is called the dissipative gap. Now we can show that the eigenvalues shown here could be grouped in a number of bands which depend on the closedness to the imaginary axis. If we denote mu j as a real part of lambda j divided by big lambda k, then the eigenvalues are grouped in this way. In quantum systems, it is rather a good thing to know about the dependence of dissipative gap on K. In when the dissipative gap closes, the whole the dynamics tend to be just a unitary one, and this may result in the creation of quasi-particles, and there could be some quasi-particle study. For that reason, we decided to look for some systems which could, for which the dependence of dissipative gap on K could be linear. Those would correspond to conformal field theories, the relativistic particles. The condition for the closure of dissipative gap is the following. Now, we have found such a system, and that is, suppose we think that we consider zero hopping, and also the zero pairing, and our hopping in our system has quite a long range, and that is sigma k depends as 1 divided by n 3 divided by 2. And also we have considered the just usual jump operator, that is the most simple dissipation we can think of. In that case, the dissipative gap closes with respect to K linearly. That could lead to, once again, some kind of conformal field theoretic things, yet we have not studied them yet. That is for the future study. Now, thank you for listening to me. That's all I have to say to you. If you have any questions, feel free to ask them.
Okay, we thank the speaker first of all, and then are there some questions or remarks?
I have a question. There is a number of co-authors for this paper. What is exactly your contribution to the work?
My contribution was to think about the Lie algebra structure of this thing. I have showed that is SL4 on C, and have found this basis. Then using this thing, we approached to the solution.
Thank you. It's quite good. Very, very interesting. Thank you.
May I ask a question? So
yes,
thank you
please.
for a very interesting talk. I want to ask the following.
Excuse me, I cannot hear you.
Sorry. What is about Lie group structures here? I mean, is it understandable what Lie group we have in this representation? I mean, if we take exponentials of these x's with all possible maybe real or complex coefficients, what Lie group do we have here? I mean. Is it understood?
I'm not sure about this question, but I do you mean that possibly some strange Lie group could correspond to this Lie algebra, but not SL4 of C?
I don't know, but so you consider the complex algebra. So I don't know exactly. I mean, for real case, if it would be SL2 of Then there are several possibilities. There are possibly spin groups or some covers of just of SL4. And here, I don't know. I just to think about, because there are different possibilities for the Lie group for the same Lie algebra.
Yet we use here only the exponentials, the regular exponentials of Lie algebra generators, and for that reason, I believe that the Lie group which we consider is just compact and connected.
Okay, thank you.
So just the message.
Thank you very much.
Mm-hmm.
Okay, other questions? So thanks again the speaker for the beautiful talk. And we will start again